Great, thanks a lot for the invitation to attend this wonderful conference. So what I want to speak about is joint work in progress with Linus, Hamann, and Fargues-Fontaine. This is sort of part of a broader program aimed at greedily adapting as much of geometric languages as possible into the setting of the Fargues-Fontaine curve and sort of new geometry. And I'm also not planning to talk about proofs. I just want to give a flavor of what's going on with the words in this title, and at least try to state it here. That's motivation. So we fix some notation. Fix G over QP, which for simplicity I'll take to be a split. I'm also going to do this thing of sort of stating some things in general, but then often telling you what it really looks like for DL2. So you could imagine for a lot of talk G is just DL2. It's still going to be new. Nice. Let me also fix a Borel. Some choice of max force decided. Later about. Okay, so what's the motivation for this? Motivation comes from thinking about the local length correspondence. State sort of as a vague philosophical hope in two different flavors. There's the classical sort of set theoretic one. Thinks that there's some kind of map from smooth irreducible representations, which for my purposes will have bar coefficients because I want to do for the tall sheaves later. You can imagine that I secretly sort of said some prayer and fixed a nice morphism of this with C throughout the talk. If that makes you uncomfortable, don't do it. Anyway, supposed to have some map from smooth bar irreps of the QP points of this group towards L parameters. Some kind of group homomorphisms from the vague group of QP towards, well, I assume G was split, so I can just take the dual group. The dual group is supposed to be some canonical finite to one map. And Ray exists, and that the fibers have good properties, and you can sort of pin something down canonically. But this is still a meta conjecture. It's a conjectural conjecture, except for not like this. But in recent times, we have enough technology to talk about this in the more categorical setting. It's very strongly analogous to many geometric languages. And here, sort of more precise expectation. So the derived category of bar sheaves on bungee. This is the same bungee as in Linus' talk, but I'll take bar coefficients everywhere. It's really actually important for the theorems to be true. So this should be equivalent by some functor. Stands for either Langlands or left adjoint. To these coherent sheaves on the stack of L parameters valued in the dual group of T. So you can make the set of these things into a sort of hardened stack in a reasonable way. That'll have very good finiteness properties. And yeah, there's a precise conjecture that these two categories really should be equivalent. And in some sense, this is an upgrade of this. So let me just, in a cartoon style, say you can relate these by this functor that already came up in Linus' talk, smooth representations of this group sort of embed fully faithfully into sheaves on G. And here you can imagine something of a different flavor. You have some L parameter that gives you a point in this stack, and you can imagine taking skyscraper. Yeah, good question marks on both. Good. Okay. Now, both of these correspondences require some small additional choice of normalization data before they are supposed to be well defined. And that's where this word Whittaker our title comes in. So both ones is normalized. So I'm going to present this in a very slightly orthodox way. So what I will encode this in is the choice of some group homomorphism lambda from my unipotent radical to GA. This morphism one. Each group. So just pinning, I suppose. Then I also want to choose psi to have a bar star non-trivial character. Okay. Then find this thing. It's kind of the key object of interest. So I denote this W psi. So this is the compact induction in the same sense as in Linus's talk. In QP points, you put radical all the way up to QP points G. And then you can get a character in here by composing psi. In usual parlance, like if Tasho Khalifa were writing a paper, he would say that B, comma, psi composed is literally a Whittaker datum, but I want to sort of unwind that composition to two different things. Okay. Any questions about this definition? A priori, this is just some smooth QP representation. Right, any other injection? But it turns out to have extremely nice properties. So let me just tell you some of them. So first of all, it's projective. So comes out of it are an exact functor on the category of smooth QP representations. And for each Bernstein block, Bernstein component. I guess I always write frac S. Well, it's not true that this is finitely generated because N of QP is not actually open in G of QP. It's sort of pro-open, but it's pro-open in a controlled way. And it turns out that the lack of finite generation is resolved in integral Bernstein blocks. So this is finitely generated. And this is due to Bushnell and Heron. And there's also some multiplicity one property hiding here, which can be incarnated in the statement that the ring of GP equivariant isomorphism to this is commutative. Go on and add more stuff to this list, but sorry, should be convincing this is kind of a nice object. Why am I mentioning it? This is exactly what you're supposed to choose to normalize these two correspondences. So let me tell you how that works. Classical. We say this one a little bit vaguely. Classical local Langlands. Part of the expectation is that remote phi, you should have a unique phi fiber. putative finite to one map with the property that I was expression. That's a quotient. And when pi satisfies this property, you say pi is I tend to use psi as a symbolic stand-in for the whole Whittaker datum, but I hope you allow that. Okay. And for experts, by most I mean tempered, but that's not where I get that. Okay. So part of the meta conjecture that is set theoretic local Langlands is that this choice of Whittaker datum should pin down whatever that upper arrow is uniquely. Okay. Right. And categorical. It should also be normalized by this same choice. And what we expect is that actually there can be more than one L, realizing this equivalence, that L depends on the L side, depends only on this choice. Somehow the normalization that it gives rise to is that if you take this functor and you apply it to the streak extension from this open point, where it's all of 1G of this representation, so now sheaf on 1G. So we do something on the stacked L parameters. This is supposed to be structure sheaf.
Does streak extension mean like it's the natural thing?
It's extension by 0.
Yeah, but with QL collisions, what does it really mean?
Yeah, so
it is the standard way that you put in representations in.
yeah, so with torsion coefficients, it would literally be streak extension in D et. With D least, because it's an open immersion, you could write I1 lower. So it's natural if you want,
Okay.
but in Peter's new motivic formalism, you can just write a streak.
But it is the same as the natural.
Yeah, but you should forget D least. D least is dead. There's a new formalism in town where this is literally the right symbol, right? Okay, and that's also why I'm allowed to take field bar coefficients in a lot of what I'm doing later in the talk, which is crucial for all of this. Other questions?
So what is it, the LC of I, and then what is the index of I?
Oh, sorry. So this Linus was writing J1 lower streak. I write I. It's this inclusion of this open point into Bungie. I1. Sits this stabilizer, this open subset. Yeah. Yeah, I apologize that I changed notation slightly. Linus was writing J and then a full one. Your questions? Okay. So if you want to try to go crazy adapting geometric Langlands constructions into this new Fargues-Scholze world, you will somehow have to face the question of how this thing and this sort of extension of it to a sheaf interacts with the sort of deeper aspects of this Fargues-Scholze story. Okay, so let me start with this vague question, and then I'll make it into a more precise question, and then try to answer it. The vague question. How is this thing? So what do I mean by the deeper parts? So the key carrier of all information in Fargues-Scholze S, say, talk, are the Hecke operators. So what are these? These are some rule which takes algebraic representation of the Langlands school group, say for QL bar in my case, produces from it some endofunctor TV of sheaves on Bungie. Okay. These are not oil. I'll give a formula for one in a special case in a second. In the sense that TW applied to TV is canonically T subscript V tensor W. If you're careful, you can also upgrade them to something where the output has a vagary action. And if you take advantage of this in totality with all the symmetries that come out of the geometrization equivalents, you can use them to construct the spectral action. This, in my point of view, this is somehow the main deep theorem of Fargues-Scholze. And I also proved this with integral coefficients, which is even harder. There's some canonical action of this on sheaves on 1G. Let me give you an example of a Hecke operator. So we take G to be GL2, okay, and I'll choose the usual upper triangular Borel. So my dominant weights are just an integer and then an integer that's less than or equal to. And for simplicity, I'll take the second integer to be 0. Okay. And let me say for experts, there's something technically annoying I have to do in this talk. There's a reason for it. Fixing from the outset a complete algebraically closed field over QP, and all my test objects live over it. Okay, so people who have studied Fargues-Scholze know that this doesn't actually change the sheaf category, but it does change the test objects. And the reason I want to do this is because now there's no asymmetry in the Hecke diagram. You don't get a div 1, you're sort of until it's specified. So I can write down what I'm about to write down. Okay, so then the diagram. Then I'll write Hecke. That's technical to say this specific flavor of dominant weight. And so what is this going to parameterize this stack up here? It's going to parameterize pairs of bundles. I'll call this H1, H2. Where I have E1 sitting inside E2 and a co-kernel supported entirely at infinity, where infinity is sort of the distinguished divisor on the Fargues-Fontaine, coming from the fact that I have an untilt fixed already in my picture. So there's no choice of a divisor, there just is one. And with length exactly n. Okay. So this is some diagram you can draw. Oh, and sorry, what do H1 and H2 do? So H1 forgets E1. H2, just forget. Okay. So you just throw away this or that piece of data. These maps are very nice. They're proper. They're homologically smooth. And in this case, it turns out that the Hecke operator, T, B, and 0, is just the n minus first symmetric power of the standard representation of GL2. This is just H2 restart. So variable sheaf here, something, same variable sheaf here, and then you have to shift it by n. Just two formal awareness. Okay, this is a little bit of a misleading situation though. For general groups and general sort of weights, there will be some complicated kernel sheaf up here that you have to take coming from geometrization. Okay, but this is maybe a constructive example to keep in mind. If n is 1, these are P1 fibrations. This is even nicer diagram. Okay. Any questions?
Is this equals by n over 2?
Yes.
And then can be odd.
And can be odd. But Linus and also myself chose the square root of whatever. So
Oh,
yeah. Other questions?
I guess you've forgotten the Bay action.
Yeah. I want to.
We're
No Vegas
not
in this
here.
talk. It's not here. I actually need to for some reason. Other questions? Okay. So just as notation, so now for any, say mu, dominant co-weight, in the co-character, in the character class of my full torus set mu to be t sub b7. Okay, so it's just some family sort of Hecke operators indexed by irreducible representations. If you like, everything can be gotten from these by composition and refractions. So now I want to make this conjecture more precise. With Clark's questions, I conjecture yet. There is this. So here's the more precise form of this question. Can we compute a Hecke operator applied to this base point sheaf in a smart way? And before I come to the answer, let me give some more motivation, because this might look like I'm randomly mashing things together, right? I told you these sheaves should be kind of important. I told you this is kind of important. Why should I care about Hecke translates of this sheaf, though? Here's motivation. And in fact, we have multiple motivations, but this is maybe the one that's best suited for a talk. Mu as on that word, find a collection of functors. So this will take sheaf on Bungie just to a complex of Gilbar vector spaces. Okay, and they'll be indexed by dominant weights. And what is the recipe? The recipe is that I take an automorphic sheaf and I map it to the external arms, if you like, from T mu applied to this sheaf extended Whittaker sheaf. So, small aside, we're doing local Langlands here. Local Langlands is one categorical level up from global Langlands. In global Langlands, you have Whittaker coefficients, which are numbers. Here, we also have Whittaker coefficients. You should think of this as sort of the muth Whittaker coefficient of this automorphic sheaf A. They're not numbers, they're complexes of vector spaces. Okay, so this is to be expected. Now I should, to harmonize my title, then we can put the word geometric here. Okay, so these are the geometric Whittaker coefficients that I promised. Okay. So here is an extremely important conjecture that the collection of all these functors to vary over mu. This gives a conservative family. Not on the whole category, that's false. Oh, sorry. Right, yes. But on the subcategory of compact objects, just as Linus' talk. Okay. So any compact automorphic sheaf should have some non-vanishing geometric Whittaker coefficient.
Or any choice of site.
Sorry?
Or any choice of site.
For any fixed choice of psi, the mu's for one choice may be different than for the other. But yes. For GLN, the choice of psi is irrelevant. Also for SO2n plus 1, where any group is connected center, etc. So
okay.
yeah.
before you said that this somehow you should only see generic things, and now everything is generic. Like what?
That's right. So I have examples for you. Yeah, this conjecture looks extremely weird at first because in classical local languages, right, we all know that only generic representations, by definition, will have a non-vanishing map from this W side, right? But what that amounts to here is the statement that, okay, the zeroth Whittaker coefficient can often be 0, when mu is 0, because the 0 Hecke operator is the identity operator, right, by the Mann modality of Hecke operators. But the higher ones can be non-trivial. So let me do an example. Let me also remark that this is an exact analog of the amazing theorem of Hamann and Raskin. 2022. Some people in this room are probably aware that the geometric Langlands conjecture and the global unramified D-modules formulation has now been proved. And somehow the breakthrough that actually made the proof happen was the analog of this being proved. Okay?
Can I ask something?
Yeah.
What does conservative mean?
It means if you have a non-zero sheaf, then for some mu, you won't get 0. Yeah. Very weak, very weak. Just that it detects whether objects are non-zero or not if you look at it for every mu in totality. Okay? I want to talk about an example because, as I said, in usual representation theory, if you write a naive analog of this, looks really false. So why does it have a chance of being true? So if G will be GL2. Here's something I can do. There's a point in Mann GL2 corresponding to the isocrystal of slope 1/2, right? So here, this group JB that Linus wrote down is the division algebra, Hermian division algebra. I can take the trivial representation. This is why I use bold 1 versus the constant. Take the trivial representation of G cross and extend it by 0 towards the rest of Mann G. And this is obviously 0 because this lives on a different component of Mann G than the Whittaker sheaf. Okay, so these sheaf supports are like completely disjoint. Okay, so this is 0. But so if you take the one of the highest weight 1, 0, same copy of QLR placed in degree 0. Okay. And when you unwind what all this fancy geometry is doing, you realize that this amounts exactly to the claim that the Grinfeld upper half space for GL2QP has a copy of the Steinberg representation of GL2QP in its first État homology group with compact supports. Okay, so up to some revolution of language, this calculation is due to Grinfeld some time ago.
But it's actually this is in a way less surprising because you're just applying doing Jackie Langlands to something generic.
Here's something even more surprising.
Because why was it the trivial representation for GL2?
I have that prepared, and I can tell you. Yeah, so, okay, maybe this is like not surprising for the reason Matt just said. What about this guy? So this is clearly 0, because the trivial representation is not generic. While n 1 or more, okay, the Hecke operator of highest weight n minus n, that sends us back to the same component. Some of the components move around according to the sum of the integers appearing here for GLN. And what this turns out to be is n copies of QL bar placed in homological degree -1. It's for all n. This calculation is extremely hard, and I can only do it by doing it on the other side of the categorical Langlands conjecture. Okay. If you can do this by purely automorphic means, let me know. And what this amounts to is that, like, if you take the trivial representation and apply a Hecke operator, one of these Hecke operators, and then restrict back to the same point 1, you're getting copies of the Steinberg representation, and those are generic.
This is a conjecture.
No, this is
Yeah,
proving.
without the thing.
Okay, but yeah, what this?
No, the calculation.
This? Well, categorical local lengths for GL2 is proved now, so it's not really a conjecture. But
Like, did you think about, maybe SL2 where you have L packets that are bigger than size 1?
yeah, I'm a little scared of SL2.
Scared of SL2.
And other questions about this motivation?
But do you know the like Chris will say like an unidentified in this copy?
I'm sure you can check it by hand by similar means.
You don't know what the actual mechanism is.
No, I mean, this is some very ad hoc thing. The second example I gave, it's a painful ad hoc calculation, even given the whole categorical conjecture. Yeah, I should say that in the G-module setting, right, this is a theorem now with Hamann and Raskin. The proof very much uses microlocal methods, and I discussed this extensively with them, and they basically told me there's no hope of proving it directly in embedded geometric lengths, which is what we're analogous to. Okay, so their methods are out the window. And
Sir, what is written on the lead point in the lower line in the right term U bar? What is
that's right, this L got carried away.
There is an L.
QL bar, and
what
then
is the
n
other?
copies. It's an
N.
n-dimensional vector space.
Now I see it.
And my highest weight is this twist of the 2n plus 1 dimensional standard representation. Other questions about these calculations? Or statements even?
I don't know, maybe this is a bit too technical, but like maybe it's worth remarking that, well, if you take like a supercuspidal L parameter and you sort of localize the Whittaker sheaf around that, then you're going to see the unique generic representation. But when you apply Hecke operators to that unique generic representation, the Kottwitz conjecture will tell you actually that you're going to start seeing all the members of the L packet.
Yeah, that's right. So you can play this the other way, and this gives more evidence maybe along the lines of Mann. What? So for GSP4, there are these weird L packets where you have non-generic supercuspidals and generic discrete series. And if you start with a non-generic supercuspidal, it's kind of analogous to my second example. You can really show by hand that there will be some mu where it has a non-vanishing coefficient, but it won't be mu equals 0. Other questions? Okay, so if you had the hope of proving this conjecture, you would maybe as a preliminary step want some kind of formula for this operation. Okay, and that formula, by the very definition of this thing, brings us back to this question I wrote here. Sort of, can we compute this in a smart way? Because then we're just sort of blowing out of it.
Geometric Casselman-Shalika.
Yeah, you need geometric Casselman-Shalika. And if you're dumb like me, it takes you 8 years to figure out what that should even mean. And then you arrive through much pain at a conjecture. So now state. Okay, so let me start with a stupid observation. Okay, so this is some warm up. Let me rewrite this I1 lower Shalika of the Whittaker thing in a way that looks a little bit more geometric. Okay, so we have diagram. Here I have bun n. Bun n is a rather weird, silly stack. In our situation, it's just point on n of qp. Okay. And then this lambda that I chose earlier gives me a map to point mod qp. Okay. And then of course you can take the trivial n bundle and push it to a trivial g bundle. And this will factor over the obvious map from this to point mod g qt. Oops. And this is side here by the usual closed inversions. Okay. So this is just the same lambda from before. Let me call this P. Okay. And if you think about what these maps are doing, push forward along map of classifying stacks corresponding to an embedding of groups. For lower shrink, it should be compact induction. For lower star, it should be normal induction. Okay. And then the last observation is that psi finds rank 1 open system here. Sorry, open system. It's the classifying stack of QP as a topological group.
Ah, okay.
Sorry, yeah,
Yeah.
experts might prefer if I'm going to underline this, but I was trying to be a little less frightening. Yeah, it has topology. Okay, so you have this diagram, and then you can check that this streak extended Whittaker sheaf is just push-pull along this diagram. So it's P over streak lambda over streak. Okay, and that just follows from staring at the definitions. Okay, now it turns out there is a version of this which suggests itself for Hecke translates the sheaf as well. So we're generally in view, as before, we have a Cartesian diagram. Bun n mu. So be careful, this is not a component of bun n. Bun n is just this one thing. This is a twisted form of bun n, okay? And it's defined using some of the maps from Linus's talk. So here you have bun b, this maps down to bun t. Bun t is a big disjoint union of things of the form point mod t of qp. Okay? Just huge disjoint union indexed by the character lattice of the dual torus canonically. And so you can say, all right, there's a component labeled by lambda, and that will have a canonical TQP torsor over it. And so here I just write point. And that point is the point covering. So this covers the mu component. Sorry, it's got a little bit slash. And then this is a definition. Okay. So this as a map towards bun B. As in Linus's talk, this is just this map P. This is now something new. I don't actually need a name for this map, but this map I do need a name for, so I'm going to call this P. Okay. Let me give an example. An example G is GL2. Mu is N0. Okay. On N mu is the stack. Be a little careful here. Well, on this for a second. It's the stack of extensions on the Fargues-Fontaine curve of O as a sub. You have rank 2 vector bundle which can vary. Then you have O minus n. Okay, besides look wrong. Minus n. Oh, yes. Right for that. Okay. So if n is 0, nothing happened. There's extensions of O by O, but if you account for the stackiness in the right way, you just get back 1 n. So this is point mod NQP. N is 0. And if n is positive, well then there's no stackiness actually, because there's no self maps from this back to this. This has no global sections, but there's an interesting H1, right? Isomorphic H1 on the Fargues-Fontaine curve of O minus n. And is bigger than 1. Okay. And what I want to observe here is that in both cases, there exists canonical map lambda mu on n mu towards the classifying stack of this same thing, point mod QP underlined. In this case, it's tautological because n of QP is QP for this group. What is it in this case? this is a Banach space of dimension n comma -1, and the -1 is a feature of the situation, not a bug. So this is geometric integral plus not fill n quotiented by a free additive action of UV underline. Okay, and unwinding that is exactly where this now comes from. Okay. Fine. Okay. Right, so in general, what can you say about this thing? So this one n mu is homologically smooth. As I'll mention, exactly the pairing of 2 rho with mu. Sorry, I'll attribute this in a second. This is not due to me. Dualizing place. Really isomorphic to, not just sort of how locally isomorphic to. Bell bar shifted by twice this number. And this follows from this really nice paper of Hamann and Imai. Okay, this is really on the nose stop of some sort of ambiguity. And there always exists a canonical map, sort of generalizing the one that we built by hand in this situation. And mu on n mu down to point left QP on plan. Okay. Maybe if you wish, close your eyes for the next 30 seconds. I'll say something about where this comes from. Sort of for each root subgroup, you can make sense of the idea of taking sort of the extension of successive graded pieces of the B bundle now that we've rigidified its T component. And what this will give you is for each single root, something in the stack of extensions, which I know H1 mod H0 of the bundle O minus sine alpha dual. And then by the same logic as in the GL2 case, each of these has a canonical map to point like the underline. And then, okay, if you have finite number of forcers for this abelian group, you can take our pair sum. Yeah, lambda makes this diagram. Okay. Lambda itself is also homologically smooth. That's a little tricky.
Explain the notation H1 over H0.
Yeah. So if the integer appearing there is 0, I mean, something you can do for any vector bundle on a curve, right? H0 of the bundle acts on H1.
Oh.
Right?
Okay.
It's the stack of extensions of O by the bundle.
Okay.
Yeah. But in this case, there's a dichotomy. If that pairing is 0, you just get 0.1 QB underline. If that pairing is 1, you get a negative BC space. And H0 is trivial. But then that negative BC space has some kind of residue map towards 0.1 QB underline. Okay? Yeah, so this is the analog of the residue map out of H1 of the dualizing sheaf on a usual curve. Okay? This canonical, in this case, this canonical map from this to one more time. So the fact that these scenes have a negative QP dimension is really like a feature of this situation for us. This is where the additive character psi will enter into the geometry, right? That -1 gives you this forcer that you can sort of twist by psi. All right, so now I'm ready to state the conjecture. I'm being a bit precise because this was very painful to decide that it should be true. For all mu, P mu I1 over 3 W psi should be isomorphic to P mu over 3 lambda mu over star of the same rank 1 thing, and then you have to shift it by. Okay, so this is some analog of the Casselman-Shalika formula in this setting. One confusion for me, at least, was that in the literature, the term Casselman-Shalika formula can mean 7 or 8 different things, and this is just one of them. And so you can start playing with this. So this is true. Mu is 0. That's not very convincing. And for GL2 and mu being 1, 0, the stalks are correct. You can do this by hand, but this already involves stuff about the cohomology of the Lubin take tower and the fact that supercuspitals appear in their multiple C1 and stuff. So this is already using sort of the full power of local languages for GL2. And in general, stalk at the extremal point in support of this thing say extremal points in the support. Agree? Yeah, it's easy to see that both of these sheaves are sort of supported on points that are more semi-stable than sort of the mu ordinary isocrystal. And you can actually compute the stalks of both sides of the mu ordinary isocrystal. It's fun on both sides and they match. But I did one more thing which really like ruined my life for a week. For GL2. And mu being 1 minus 1 supercuspidal part of stalk at 1. That is right. So here you know that each, when you do that, okay, maybe PGL2, so there's no central annoyance, then every supercuspidal will appear in that stalk with multiplicity 3 on this side, and you have to convince yourself that if you stare really, really, really hard at the geometry and suffer a lot, you'll actually get that thing out. Okay, so at that point,
So you're saying stalks are correct, but that means you don't have a natural map that you're.
And so this is all like some preliminary stuff, right? And then,
So
yeah,
is this conjecture theorem now?
that's the punchline of this talk.
Yeah, but so this all this is history.
Oh, this is history.
We can forget
Having you share my suffering a little bit. Yeah, you can forget history if you wish. That's not usually a good idea in
Theorems
human
require
existence.
conjectures. So.
Needs to problems of other kinds. Okay. Right. Oh, can I erase? Right, so I somehow convinced myself that this should probably be true, but the reason I was hesitant was that at some point in this process, I realized that there's a canonical map. So there's a canonical map from the right side to the left side. And this made me really optimistic. And where does this come from? Well, this sheaf on the right is just some pullback push forward, right? And then a Hecke operator is another pullback push forward. And so you can start just trying to use proper base change, sort of go on your merry way and compute that composition. And when you do, you get a fiber product diagram of bun n mu over bun g with some Hecke stack, okay? And there's one piece of that fiber product which sort of is comprehensible, okay? And if you unwind what's happening on that one piece, sort of corresponds to filtering the Hecke stack by the open Schubert cells rather than their closures. You'll see that on the open piece, you get this, okay? So there is some canonical map coming from excision, but the cone of this map is a huge mess. Okay. Some completely weird intractable sheaf on this Hecke stack, but it's apparently it has the miraculous property that if you push it down to bun G, you get 0. Okay, sort of the final push along the second leg of the Hecke diagram. And if you try to do this directly, just sort of roll up your sleeves and do this, doesn't work. Okay. This mess. Even for GL2, this doesn't seem to work by sort of direct thought. 10 minutes. Yes, thank you. Okay. Right. So here. As Mr. Greenfeld asked, the conjecture is true.
Once the conjecture is true, how close is one then proving the conservation?
Far. Yeah. So, digression for a second. Casselman-Shalika, as I said, comes in like 7 or 8 different forms. This is some kind of global on the curved form of it. There's also a local form, which I'll hope to allude to by the end of the talk. The local form comes in many variants. You can do it over a geometric point, over the curve with varying point, over 20 copies of the curve, over rand space. You can do it with other adjectives like factorizable and stuff. And somehow for applications, which do bring us closer to like categorical languages, these fancier versions turn out to be important. And that's actually our main motivation, is to prove something about how Eisenstein series interact with like the 2 different sizes of this categorical conjecture. And because this Whittaker sheaf is how it's normalized, you have to know something about how, well, how the Hecke operators interact with that, but in a very like universal way over rand space in some sense. Today I'm saying the least fancy part of the story, and the most fancy part is somehow what's needed for applications. But somehow this motivating conjecture is still of key importance. So let me state as a corollary,